Good morning, everyone. I'll share screen now.
Good morning, sir.
Good morning. Good morning. We were looking at. Wait, just a second. Okay, we were looking at some examples of martingales, and the first example was the independent of sums of independent random variables. Then second is the variance of a sum, and the third one is something which is coming from Markov chains, what we had called bounded right regular sequence for the transition matrix P. And this we had looked at. And today we will look at something which is similar to the previous one, as a matter of fact, slightly more general. So this is, we will say, a martingale induced by right eigenvectors of transition matrices. So let y0, y1, y2 be a Markov chain, and the states is assumed to be finite set, yes, and transition probability matrix is P. So P is supposing the order of the matrix is K, P will be K cross K matrix. So there can be at most K eigenvalues, and some of them may have multiplicity, the multiplicity may be greater than 1 and so on. So let F be a right eigenvector. So the earlier example which we saw was corresponding to the eigenvalue 1 and the right eigenvector corresponding to that. So here it can be any eigenvector, right eigenvector. So which means it is just like that right regular that sequence. So instead of earlier we didn't have that lambda was equal to 1, so it was that equation. Now with that lambda. So lambda times Fi is equal to summation over j Pij Fj for every j in S. So that is what F is. So in this case, we take Xn as lambda to the power minus n, that is 1 over lambda power n, times Fyn. So our candidate for being a martingale is Xn. And you know that the martingale has an important property that the expectation doesn't change. Expectation of Xn equal to expectation X0. So that is why this factor is included here. And since S is a finite state space, there is no problem about mod Xn being integrable. That is, expectation of mod Xn is finite, and therefore expectation of Xn is a finite number, maybe negative. Note it down if you want to. Okay. So the proof is something along the similar lines as in the previous example. So let n be an arbitrary positive integer, and I0, I1, In minus 1, and I are elements in S. So using the Markov property and that defining equation here, one sees that conditional expectation of lambda to the power n plus 1, F y n plus 1. So, okay, that is your Xn plus 1. So that conditional expectation given y0 equal to I0, etc., yn minus 1 equal to I sub n minus 1, yn equal to I. So here, as before, this equality involves a couple of steps in between that I leave it to you to check. So actually, I should have again written that using the Markov property and this thing, verify that. So in mathematics, whenever we say easy to see that we can obtain all those things are just exercises, small exercises. So you write this conditional expectation in terms of, let us say, this taking the value some k and then summation over that times this probability that this equal to k given this, that conditional probability. And when you take that conditional probability, you can apply the Markov property. So then all these, the n things will not be there. What you will have is, say, let us say, j times summation over j, this equal to, let us say, j given yn equal to I. Actually, you will basically get this. And that is precisely Pij. And also you write lambda to the power minus n plus 1 as lambda to the power minus n and lambda to the power minus 1. So then you easily see this is equal to lambda to the power minus n fi. So now you recall the way we have defined the conditional expectation as a random variable. When you have this thing, conditional expectation of that thing, given these things equal to this, especially given yn equal to I, if it happens to be this way, then the conditional expectation is instead of I, you plug in xn. Or rather, whatever that yn, sorry, you should plug in yn. And that precisely turns out to be your xn. So please treat this as an exercise, work it out. And similarly in the previous example. So whatever I mentioned orally is what is written here. So this therefore is, you are appealing to the way conditional expectation is defined as a random variable. You refer back to the earlier notes. So this shows that xn is a martingale with respect to that yn. Note it down, please. Okay. This is a comments. Example 3 is a special case of example 4 when S is finite. Remember that in example 3, we did not assume the state space is finite. So if you assume the state space need not be finite, you may not be able to bring in eigenvalue and things like that. Those things, it might have to be done very carefully. So eigenvector, etc. So instead, you can again use the definition like a right regular sequence and so on. And you can extend. So to ensure this, you will have to make some assumption. For example, if it is bounded or something like that. Okay. The next example is known as Wald's example, Wald's martingale, named after Abraham Wald. So let y0 be 0 and y1, y2 a sequence of IID random variables such that it's that yi's have moment generating function for some lambda not equal to 0. So that means basically in a at least in one side of the neighbor, this thing 0, half neighborhood at least. Lambda can be positive or negative. Then you take x0 is identically 1. Of course, that corresponds to e to the power this y0. And xn is e to the power lambda times the summation yi up to I equal to n. And divided by this phi lambda to the power n or phi lambda to the power n. So here sort of you can see that these xn's are getting multiplied. No, that is, it is not a, of course, basically it is e to the power some additive thing, but so it is an exercise for you to show that this is a martingale with respect to in. Please note it down. Okay. So we give a slightly extension of the definition of martingale, which are called sub-martingales and super martingales, which turn out to be useful even to study martingales. Of course, the martingale theory we will not be doing much, but especially when one considers convergence theorem, which we will not be doing, you will see these things play a major role. Okay. So as before, xn and yn be stochastic process. Of course, one dimensional, discrete valued, and so on. So here, remember in martingale, the defining property was an equality. Here, these are going to be not equalities. So, and there, in that case, when the defining this thing was an equality, from that definition and the what we know about conditional expectation, etc., it turns out that xn is a function of y0, y1 up to yn. So since here the defining property is not going to be an equation, we have to assume a priori that xn is a function of y0, y1 up to yn. Or in some context, you want to use submartingales or supermartingales. From that, you should be able to derive this. For example, if your submartingale or supermartingale is going to come out of the martingale, then because of the other one being the martingale, this will be a consequence. So that is the first assumption. Of course, the second is the standard thing, second and third. So, I mean, second is standard. The third is the defining property. The expectation exists, which means expectation of mod xn is finite. And here, the defining property is that conditional expectation of xn plus 1 given y0, y1 up to yn is less than or equal to xn. Then one says this xn is a super martingale with respect to yn. Okay, note it down, please. So you realize the importance of the first thing, the first assumption. Of course, second assumption is to ensure that the conditional expectations are well defined. Remember that conditional expectation will be defined, we had assumed that. Or rather, we need to assume. Okay. In the case of submartingale, 1 and 2 are the same. And in the third, the defining thing, the inequality gets reversed. So here it is less than or equal to, here this is greater than or equal. Okay. So as before, we will omit any mention of these yns if it is evident from the context or if it is not important, etc. etc. Of course, from the definition, it's very clear that xn is a super martingale with respect to yn if and only if minus xn is a sub martingale. Also, xn is a martingale if and only if it is a super martingale as well as a sub martingale. These are all very immediate and obvious consequences. Note it down if you want. All right. Now, we just, many of these things concerning convex functions, you might have seen by now in many courses. Convex functions are important classes of functions. So here also, they turn up. And one simple reason is that certain functions are obviously, I mean, we know that convex. For example, x going to x squared is a convex function, a quadratic. And so on. So as you know, this function is in some of you might have even seen convex functions on higher dimensional spaces. So since we are considering here only one-dimensional situation, let I be an interval. Of course, basically we only what to choose is a convex set, and on the real line, the only convex sets are basically intervals, maybe infinite intervals. So if fx convex, it's a defining equation. If x1 and x2 are points in the interval, and alpha is a number between 0 and 1, of course, you can include 0, alpha equal to 0 as well as alpha equal to 1, no problem. Then alpha times fx plus 1 minus alpha times f at x2 is greater than or equal to f evaluated at alpha x1 plus 1 minus alpha x2. And using induction, it is usually an exercise after definition of convex functions. One can show convexity holds if and only if you have a convex combination. Instead of just choosing 2 points, you choose, let us say, m points, and you choose m alpha I, such that these alpha i's are greater than or equal to 0, and they sum up to 1. Here we have, of course, this thing that is also greater than or equal to. So that same thing can be used here. Yeah, maybe you should make a change here. And also always the picture you should have in mind is take the graph of that y equal to x squared or something, and join the card 2 points between any 2 points on that graph, and the value of the function at the this thing is less than the value of the card at that point. That is the pictorial way of defining convexity in the one-dimensional case. Note it down if you want to. So all these things you are familiar with. Yeah. Just mentioning that the I can even be an infinite interval. Okay. So if x is a discrete random variable, let us say the alpha i's, they are non-negative and they sum up to 1. So that can be viewed as a probability measure. And probability measure which of a random variable which takes values in x1, x2, xm inside that interval. So if you have a discrete random variable which takes these values and the value xi with probability alpha I, then these summations can be interpreted as expectations. And that precisely is what is being done. And once you do that, that gets the name of Jensen's or Jensen's inequality. And one more fact you would have seen is that a twice differentiable function f on the interval I is convex if and only if the second derivative is non-negative for all x. Excuse me. Many of these things you can refer to books on analysis, especially you can also refer to books on optimization. As many of you might have seen, in optimization, convex functions play a big role, very central role. Okay, the result, Jensen's inequality, or Jensen's inequality. Let f be a convex function on the real line. Let x be a random variable such that expectation of mod x is finite, as well as expectation of mod fx is finite. So remember that here we have mentioned that this can be viewed upon as expectation of f of x, and this is f of expectation of x. So we want to make sure that these objects make sense. So that is the idea of assuming this. So then the inequality is precisely. So we will prove it assuming for the further assumption that f is twice differentiable. So that the proof is easy. Okay, since expectation of x exists, let us denote by mu expectation of x. Sorry, if you please want to copy down, please do it. Yeah. So let mu denote expectation of x and expand the function f. It is twice differentiable. So use the Taylor series with remainder. So f of x is f of mu plus f prime mu at f prime at mu multiplied with x minus mu, and the remainder term is half f double prime xi x minus xi whole square, where this is a point between x and xi. I mean x and x plus or x minus xi. X and that mu, sorry, it's a xi is a point between mu and x. Yeah. And since this is twice differentiable convex function, this guy is greater than or equal to 0. So we have this. So since this happens for every value of little x in the interval, and you can replace it by x, that is f at x omega for every omega is greater than or equal to f mu plus f prime mu at x mu x omega minus. So now take expectation. So when you do that, you have expectation of fx greater than or equal to expectation of this whole thing. And this is a constant which comes out. And this is also a constant which comes out. And here you have expectation of x minus mu, but that is 0 because mu itself is expectation. So this completes the proof. And again, you substitute back mu equal to expectation x, you get what you want. Note it down if you want. So this says that Jensen's inequality is valid for conditional expectation also. And it is in this fashion we will be making use of it. So let x and f be as in Jensen's inequality. So f is a convex function and x is a discrete random variable which takes value in the interval I, and f of expectation of x as well as expectation of x exist. And basically for that you use what we had done like earlier, the conditional expectation of x given y1 equal to or x1 x0 equal to this thing and x1 equal to I1 and so on, and xn equal to in and things like that. Rather it is yn, right? We are using y. Yeah, and similarly here, and then prove the appropriate. Yeah, this is what you consider the conditional expectation of these guys given specific value. You express this in terms of the conditional probability and fx equal to j or something like that. Use the definition of x conditional expectation in terms of conditional probability. So with respect to the conditional probability, etc., also the Jensen's inequality is valid. And therefore you get straight away this. Remember that here you don't need any Markov property, or rather you don't have any license to use Markov property because the YAs are not assumed to be Markov. So we have means verify that. So we get, note that are all dangerous words. They are sort of words which are mined. You have to sort of unearth that. Words are phrases which are mined. So we get this for conditional expectation also. Note it down. Okay, one result. Let xn be a martingale with respect to yn. So let f be a convex function on R such that the expectation of mod fxn exists. Of course, we are assuming xn is a martingale, and in the definition of martingale is inherent that expectation of xn exists, which means expectation of mod xn is finite. And f is given to be convex. So Jensen's inequality can be applied. Then the conclusion is f of xn is a submartingale with respect to yn. So that means f of xn will satisfy a property like this. Okay. Yeah. So fxn is a submartingale with respect to yn. So since xn is given to be a martingale with respect to yn, xn for every n, fixed n, xn is a function of y0, y1 up to yn. And fxn in turn is a function of xn. Therefore, f of xn is a function of y0, y1 up to yn for any given n. So that first condition in the definition of submartingale is satisfied. The second is satisfied because we are already given this. So the third thing is what we have to verify. So, yeah, obvious consequences of this conclusion is that in particular, mod xn is a submartingale. Mod xn, x going to mod x, is a convex function. Of course, it is not differentiable at 0. But our proof of Jensen's inequality, we have given only for twice differentiable functions. The result holds for any continuous convex function continuous. Also, if xn is already given to be square integrable, then expectation xn squared exists, and it turns out to be that if xn is a martingale, xn squared is a submartingale whenever the xn is square integrable. These kind of results also prove to be very useful when convergence theorems and things like that, if mean square distance is involved. That is, as one says in analysis, L2 distances are involved. And there the results will basically concern submartingates also. Please note it down. The proof is once. So Jensen's inequality we have at our disposal. So that also for the conditional expectation we have mentioned it here. And assuming Jensen's inequality, proving it for conditional expectation, it also holds is simple. And of course, proof of Jensen's inequality, we have given it only when the function is twice differential. Though the result holds for general convex functions, which are of course obviously continuous. So use Jensen's inequality for conditional expectation. Then we have this, and that's it. And here we are using xn is a martingale, the last equation. So that proves the first assertion. The other two assertions are obvious. So that is all for today. I think next time we will start with stopping times. Of course, in the context of Markov chains, you have already seen some, and you will also, if you want me to go back to any slide, I can do that.
Sir, so how many more lectures will you take?
I might go on maybe till the end of next week or middle of next week.
Okay.
That is what I plan. And also now that you have raised this question regarding your final exam, I plan to have it on 29th or 30th of December.
29th to 30th of December, final exam.
Yeah, that is what I hope to have it, because till 28th, I might be busy with other things.
Okay.
Okay. So I will send an email to all of you, probably say whether it is 29th or 30th. I would also like to have it in the morning, maybe 10 to 1 or something like that. So depending on whether it's a 2.5 hour exam or 3 hour exam and so on. And just alert some of your friends. Anyway, I will send an email in a couple of days.
Okay. So will you give us sufficient time before the end term for revision?
Yes, because you may have 2 weeks now.
Okay, 2 weeks. Okay.
Since see, I am taking 3 classes per week.
Okay.
And certain things I feel it, say for example, I was initially planning to do something concerning Markov decision processes. Now I have sort of suspended that plan.
Okay.
So anyway, very often that's what happens, because we become a bit ambitious. And also the relation between Markov chains and the eigenvalues of the transition matrix for finite, of course, finite state spaces. So there is a long theorem involved, Perron-Frobenius theorem, and some of these things are some consequences, but some consequence which concerns the rate of convergence you have already seen through other methods. So there, how to relate it to eigenvalues, I thought of that also requires some conditions. So I thought I shall not press on that. Okay, those are all again interesting aspects. So again, I repeat that many of these courses are not meant to make you sort of just stuff you with a lot of knowledge. I prefer, I hope, and I mean, rather, I am satisfied if this enables you to gain confidence that you can do the subject by yourself later on, if need be. Okay. So if you don't have any question or anything now, we can end the session.
Okay, so the lectures will be most probably over by 2nd week of December, right? 2nd week of December.
I hope so.
Hope so. Okay, fine.
See, everything is now hope.
Okay.
because we don't know about deltas and omicrons and all various other Greek alphabet suffixes, right? Given the various conditions. Okay, take care, all of you. Good luck and see you next time.